all objects floating at the surface where interfacial effects are important. So here's our object. And we have an interface, a blue interface. This is cute. Okay. This is going to match onto horizontal, likewise here. It has a radius r, and we know that these things are going to be menisci if they can exist, and they're going to have a characteristic scale of the capillary length. So we know there are two basic forces that are going to act on this. One is interfacial tension, and we know immediately what that's going to be. So it's basically going to depend on this angle, right? It's going to depend on, we know the magnitude of this is going to be surface tension, so it's only going to depend on the local geometry of the interface. So we can call this angle, say, theta. And that, of course, can be related to the contact angle. And then there's going to be the hydrostatic pressure, right? And hydrostatic pressure we compute just as we did previously by integrating. We calculate the hydrostatic force by integrating the hydrostatic pressure over the surface in contact with the fluid, which is this surface, right? So we know along this surface there's everywhere hydrostatic pressure, which is decreasing as you get closer to the surface. Right? So this is P naught plus rho GZ, if Z is now our distance from the surface. Okay. So those two forces are going to be the net force acting on this floating body. And the question is, when is it going to sink? When is it going to float? Okay, so the force balance so let's say this thing has mass m. So we then have to integrate so let's just imagine for the moment this is a two-dimensional body. It extends simply to 3D, but then we'll just have a line integral over a curve C. So this is our curve C now, this green guy. So basically this is then the line integral of the pressure over the base. And then we have the contribution from the ends here. Okay, and so this one's going to depend on gravity. This one's going to depend on surface tension. So again, the relative magnitude is going to be prescribed by basically by how big the object is relative to the capillary length. Okay, so, and the buoyancy force, so this is the buoyancy force. So I'll just mention, I have in the notes, it may confuse you slightly, but I computed sigma div of n along here. It turns out if you have a super hydrophobic surface, then you can think, well, perhaps what's acting is there's a jump in curvature. So if there is no interface, right, then you can calculate the pressure along the surface as sigma div n and integrate it. And when you do that integral, use this Frenet-Serre equation, which I'm going to introduce in a second. But it turns out that integrating sigma div n over the surface of the body simply gives you this result. It gives you it can be accounted for entirely by the contributions from the end. So I'll just write down the contributions at the end. We'll show you that in a second. So what we're going to do here is we're going to compute the force acting along this length. So this is the buoyancy force, this is the surface tension force. So let's compute the buoyancy. So this just looks exactly like our what we did previously. So we're basically going to integrate rho g z and dl along c. So this just gives you the weight of the fluid displaced above the body. Okay? So this volume is the volume displaced above. Okay, so the buoyancy force, right? By integrating the pressure along this bottom, rho gz, you simply get the weight of the fluid displaced above the body. Okay? So it's above the body, but inside the contact line. So again, so these are the contact lines here. Okay, so if this was, so this would suggest that if this was all there was, then Archimedes' principle would have to be revised, right? But Archimedes actually got it right by accident, because we'll see that this surface tension force is going to be precisely equal to the weight of the fluid displaced outside of the contact line. Okay?
So you have the volume of the, let's say, the part that is on top of the contact line.
Yeah.
Depending on the geometry of the body, I mean, the body could have a part on outside that area, right? Even in that case, right? Because those two verticals could cut the body.
Yeah, they would. Yeah, I think it's so. If you mean if you have a shape that looks, if you have something like that.
No, I mean even in this case, the verticals you draw, they could be slicing the sphere, leaving a little casket on the sides. You know?
Yeah, well, like this, right?
Yeah, like that. Yeah.
Okay, sure, yeah.
That's an exaggeration of what you're saying.
Okay.
Yeah.
Yeah, I was thinking leaving the body, the part where it's in contact with the air, I'm saying. Because that would be interesting, because that would be pulling down and not being pushed.
Yeah, you can think that one through. I haven't thought it through. Good homework problem. Okay, so the curvature force, the surface tension force is this. So one thing we know at the interface, so outside of the contact line, we know that there's a balance between hydrostatic pressure and curvature pressure, right? We just did that calculation for the meniscus. So we have Young Laplace. Okay, so if we integrate these pressures along this meniscus, we know that integrating rho gz along here is going to give us the weight of the fluid displaced above the meniscus and outside the contact line, right? So that's what we're going to get by integrating this along the curve, and then the question is what we get when we integrate that along the meniscus. Okay? And this is something that no one ever taught me. Had to learn on the street. For Frenet-Serre, but okay, so we're going to integrate outside contact line. So this is the vertical. So we're basically now integrating the hydrostatic pressure everywhere along here. So it goes to 0 here. Oops. We have some continuity problems there with our green arrows. But you see the hydrostatic pressure is getting higher there. We integrate this. So this is the contribution to the force on the interface coming from hydrostatic pressure, and that rho g Vm. So Vm is the volume of fluid displaced get a new color here, yellow, orange, okay. Okay, so Vm is actually, so these two. Okay. And since there's no weight to support, that has to be balanced. So we have this upwards force, and that has to balance the tensile force coming down. Okay? And we can see this curvature force so we know that there's, so we just integrated this and took its vertical component along the interface, and now we're going to do the same with this. So let's call this F. So this is F buoyancy on the meniscus. So F curvature on the meniscus. So we just take the vertical component of sigma div n dl. Okay, and we have to use a little trick. So this is the Frenet-Serre equations. Which are in the appendix, as I recall. I hope they are. Yeah. So if we have a 2D interface, we have the normal n and the tangent t, then they're related. We can express the divergence of normal dt dl. So L is an element of arc length. Okay, so the rate of change of the tangent as you move along the curve is given by this. Okay? And this is actually very handy because this is none other than the curvature pressure, right? Times the local normal. Right? And the other one, which we won't use quite so much, div n t equals, so this is the rate of change of the normal with arc length is given by this. But we're going to use this one immediately here. We see that we can simply substitute this in. We're integrating now along this contour. Sorry, I should have done this. So this is now a contour C. Okay, so using Frenet-Serre, we can write this as sigma z dot c of the meniscus, so dt dl. So it is, you can see, integrating the curvature pressure along the ends just gives you the contributions from the ends. So Tx, let's just define these, minus T2. So Tx and T2 is basically this guy. Okay, so that's the tangent at one endpoint, and this is the tangent at the other. Okay? And so this has no vertical component. So the vertical component is simply going to be this guy again. So it's sigma sine theta. Okay, so what did we just do? We basically integrated the curvature pressure along this arc, right? Because in some sense, if you want to calculate the force acting on the body, this is what you want to do, right? You know, there's curvature pressure acting on the surface, but we found that doing that, integrating sigma div n using this Frenet-Serre simply gives you that the net force can be computed from the endpoints. Okay, so this is kind of a useful thing to have on your fingertip. So if you want to calculate the net force resulting from an interface, you can just worry about what happens at the ends. Okay? Okay, so this is telling us this surface tension force is precisely equal to the curvature force. This is equal to the weight of the fluid displaced outside the meniscus. Right, maybe I should do one last step. So what we're doing basically is we've just integrated this along the surface, and so we can basically compute, equate these two things. So we can say rho g v m. So that's the weight of the fluid displaced by the meniscus is equal to 2 sigma sine of theta. So this is the weight of fluid displaced outside the contact line. Okay? So normal integration of rho gz gives us the volume of fluid displaced inside the contact line. And then this we've shown is equal to the weight of the fluid displaced outside the contact line. Okay, so Archimedes is vindicated. And we can see not only have we vindicated Archimedes, but we've seen what the relative contributions are from buoyancy and from curvature. So Archimedes' principle and if you really like geometry, it'd be very interesting to try and generalize what Archimedes did for looking stability and so forth of floating bodies for the case where surface tension forces are important. Okay, we've also seen, so we can look at the contributions from buoyancy over curvature in weight support. So this is FB over FC. We've seen that those are expressible in terms of volumes of fluid. So this is simply given by the volume above the body and the volume above the meniscus. Okay? So what do we know? We know what this length scale is. What's this length scale? Right. So we know that's roughly the capillary length, and there'll be some fudge factor depending on the contact angle. In general, so if this is we've sort of posited this, I've written this down in 2D, so we imagine we have a long cylinder, say the leg of a water strider or a paper clip sitting there, right? So we can assess the relative magnitudes of these two forces, and so see which one is important when. So this basically is going to, the top one is going to depend on the body scale, which we've said is R, and this one is going to be the capillary length. Okay, so we see immediately that surface tension is going to dominate the weight support for small objects. Okay? So if we have an object which is small relative to the capillary length, so the leg of these water walking insects is around 100 microns, so they're getting 10 times the weight support from surface tension than from buoyancy. Okay? Okay, let's, can we turn that on again? So the nice thing about these surface tension problems, you can always, it's like when you look at any fluids problem, the first thing you ask is what's the Reynolds number? And then you decide whether inertia or viscosity is going to dominate. And then the second, if you're looking at an interfacial problem, you say how big are things relative to the capillary length? And that'll prescribe what's dominating the system, whether it's surface tension or gravity. Okay. Too easy. Okay, so this is by the way, this is generalized to Joe Keller was interested in this problem because he Joe Keller is a very famous applied mathematician, no? And he spends all of his summers on a Woods Hole, which is a nice place off the coast of Massachusetts, and they have a summer school there every year. He's there, and they have tons of water striders, so he's interested in water walking insects as well, and got into his problems with that. But he just generalized this to 2D, so all of these conclusions hold. Well, I've just done it in 2D for the sake of simplicity. Okay, so but these small creatures are supported by surface tension, so whether or not they can reside at rest depends on how on their weight. So basically, you know, if P is their total contact length, so you get by combining all of the lengths of their legs in contact with water, if their total weight is less than this, then they can stay afloat. Because basically buoyancy contributes almost nothing because their legs are very small in dimension relative to the capillary length. Okay, so these guys, you can see, I mean, because the question is you're competing, you have surface tension acting like this, and then you have rho gz, but the deflection is very small, right? So the the hydrostatic pressure is really quite small if they're deflecting it very little. Okay, and so you can ask a more complicated question about biomorphology. So we know that the surface tension force which is available for weight support is going to go as their length, whereas their weight is going to go as their length cubed, right? So you can ask then, for these creatures, what is the dependence of the form on size? So do their legs scale, are they isomorphic? As they get bigger, does their shape change? And you expect that they might, because as they get bigger, their weight gets larger, so you think that maybe their legs have to get longer in order to maintain their position on the interface. And so my student dug through the literature And the biggest, so there's a Vietnamese water strider, which is 14 centimeters in length. It kind of looks like this. So it has very long legs. And this is required. So basically, this is the dependence of the surface tension force on the weight of the object. So basically, if they're going to stay above the surface, they have to be above this line. Okay? And you can see that they're safely above the line, very safely above the line when they're small, but as they get bigger and bigger and bigger, they get close to the edge. And this is basically the limit, which is this Vietnamese water strider, which is very close to the edge. But you also see that if they were isometric, that is to say, if they're if their weight went with their length cubed, so the contact length cubed, you would have the things would fall along this line. The fact that they don't, the fact that the slope is higher, is indicating that as they get larger, their legs are becoming proportionately longer. So nature has figured out how to work most efficiently. Okay, so so we've sort of been looking at considering the shapes of menisci, so looking at considering force balances at the interface, and also the so basically looking at pressures. You can also think about energetics. So the system, all of these systems are acting in such a way as to minimize the total energy in the system. So the total energy, which we consider is the energy, so there's an energy of wetting. So this is basically comes into the contact angle, and also there's gravitational potential energy and there's surface energy. Right? So these are you can formulate the system as an minimization problem. So if we have things now floating objects, so imagine bubbles at the surface, we know that they're generating anomalous surface energy, right? They're basically pulling upwards locally on the interface, and this is creating anomalous surface energy and gravitational potential energy. Okay, and so then the question is, what's the minimum energy state? So if we have these two bubbles here, we can compute the total energy of the system, and if the total energy of the system decreases if they move together, then they will move together. So basically, what you want to do is calculate the the energy in the system as a function of the position of the bubbles, and then the gradient in that force as a function of x will give you the force acting on them. And so we know, one thing we know right away is that the range of interaction is the capillary length, right? Because we know that these things, the menisci only extend to a capillary length, so if they're separated by something much bigger than the capillary length, then they don't feel each other, right? So it's a local effect. They basically deform the interface locally. If they're far enough away, then perturbing them one way or the other is not going to change anything. So it's only these capillary forces have a limited range, and that range is the capillary length. So similarly here, if we have a particule, where did that come from? That's how the French write it. So I must have put it in as a joke many years ago. So if you have a heavy object there and a light one here, they're going to repel in order to, again, minimize the system energy. But the system energy, again, it's gravitational plus curvature. So it's not exactly obvious which way things are going to work, but it does make sense. If these things come together, then you can get a really huge amount of interface here, right? So, but again, there's this limited range of interaction, which is the capillary length. So this is how you rationalize, beer bubbles, bubbles in champagne forming rafts, simply to minimize the surface energy. And this is actually being used, so people have looked at this, so they're now interested in constructing things on a micro scale, and this is what George Whiteside's group at Harvard, they've been constructing using flotational capillary forces for self-assembly. So you can basically have a drop of fluid with little particles on it, and then as the drop evaporates, these particles will come together and form assemblies, and then the fluid will, of course, evaporate away, and you'll be left with some rigid microstructure. Okay, so again, in terms of how you formulate it, you have to minimize the total energy of the system, so you write down the energy functional, which has a surface energy component, which is simply the surface tension times the area, right? So that's the surface area, and that's going to explicitly depend on R. And then there's the gravitational potential energy, which just has to do with how much fluid is displaced vertically. And so you can calculate so these are two floating objects now. You can calculate the force on them as a function of R by taking the derivative of this energy. And so you can see then how things go and when they attract and when they repel. Okay, and so that's how we can rationalize this sort of behavior. So again, we now have a object which is heavy relative to water. It's basically copper. And it's, we can say why it floats now because of surface tension, why the attractive force, because the system's acting to minimize surface energy. And who cares? People who produce things on a microscale can use this for self-assembly. And again, see, so it's just bare. It looks a little outside the range now. They're just getting within range, and then it starts moving. But if it's far enough away, then they don't feel each other.
John, it looks like it's really something that it aligns also, not only glue.
Yeah.
It aligns. So the tips. What is the mechanism for alignment at the tips?
So
it's got to be surface tension too, but in which way?
Yeah. So it's actually very interesting, like how to optimally pack things. And nature does this. There are these floating, like larvae of various insects, and they basically will pack on the surface, and they'll attract each other. And how they pack depends on their shape. But it's sort of, there's a capillary packing problem that some people have looked at recently. But it's sort of non-trivial. If you make things,
I could see it did a little adjustment in the line, right?
Yeah, exactly. So that is presumably the minimum energy state. So one would have to prove that.
Size, like that size is a little bit different. It will align on one of the sides, right?
Right. Yeah.
And which side will it?
And yeah, because if you have things which aren't rectangles, right? If they're prolate ellipsoids, how are they going to pack? Right. Not clear.
Not clear.
Yeah. And so again, this is how these guys attract one another at the interface and stay together. And so you'll get these large assemblages of these bugs. They'll basically be out in a windy sea and they don't want to get lost, so they'll all lock together at the surface using capillary forces. Okay, so the last thing I want to do is, oh wait, we only got 10 minutes. Maybe I'll just give you this problem as a homework problem.
Those ducks, they're using chemical gradients, or is it just?
No, they're just walking. They're just walking on the surface. Here we go. Okay, so this is the problem that I want to give you guys. Capillary rise in a wedge. Okay, so what you're gonna see here is you have two plates. So maybe I'll solve this in the time remaining. No, that's okay actually. So basically, you have two glass plates which are connected at a corner. So they're basically like this, right? And you're looking from the side. So the spread between them is basically increasing with distance from this left-hand side, and you're going to touch this down on the surface of water. So you're going to get capillary rise. The question is, what does the what does the shape look like? Right, so the plates are close here and far here and increasing linearly with distance from this corner. Okay? So can we rationalize this shape? Okay, now we can get the lights. Okay, so this is x, and we saw that the shape goes like this. It basically looks like a hyperbola. Okay, so you see the geometry there? Okay, so next day, by the way, we're gonna do a few more static-like problems. Then we're gonna work through capillary rise, which is a very important problem in all sorts of applications. Okay, so we have so the divergence of the normal, so there are going to be two components to the curvature. There's going to be this component, and then there's going to be the component across the gap. Okay? So, and across the gap, that curvature is going to be much larger. Right? So it's going to basically scale with 1 over this distance, whereas this one's going to go like something large. So this is, you can call this radius of curvature here is like R, and across here you're going to have a curvature which is basically, you know, like 1 over so it's going to go like 1 over t. So 1 over t of x plus 1 over r of x. So this is the curvature across the gap. And this is the in-plane curvature. Okay, so if we have a narrow gap, then we say our curvature is basically going to be 1 over t. So normal stress okay, so this gives us the shape of the interface. Okay, so we can actually get a rise which is considerably greater than the capillary length. And in general, if we actually look at this carefully, then we're looking across the gap now. In general, this curvature is going to depend on the contact angle. So this is our contact angle here, theta E. So this is our fluid phase, and this is the air. So theta E. So note. So this in the curvature across the gap depend on the equilibrium contact angle, in particular delta P. So you can think about how to rationalize this. You'll work through this on the homework, but basically it's going to scale like this. So the curvature across a gap is going to depend on the contact angle, right? So you have to have constant curvature here, and you have to match onto this contact angle. So This will give you a slightly revised estimate. So there's some suggestion, some friends of mine are looking at hydraulics in trees, and the shapes of different cells in trees may determine their efficiency in transporting fluid. And sometimes there are bubbles forming, and the question is how you fill the voids. And there's some suggestion that the trees with very large trees have a different type. The shape of the cell in cross section is different than for smaller trees, and they actually exploit these geometric effects which you get from corners. Okay, any questions? No.